Math 2415, section 10.7, vector functions. One more eliminating the parameter strategy. Now, I'm not saying this is the last one you'll ever see. I'm just saying I'm going to show you one more right now. We're going to eliminate the parameter, we're going to graph, and we're going to include the orientation. But unlike the previous two examples, I'm not going to draw the graph first, because sometimes the best way to sketch the graph of a vector function is to set up its parametric equations, eliminate the parameter, and then examine the rectangular equation. For the purposes of this video, assume rectangular equation means it's an equation involving x's and y's only. And then from the rectangular equation, sketch the graph and then determine its orientation. Our vector function in this case is r of t equals 2 sine t, 3 cosine t. Now, could we use the first strategy for eliminating the parameter, solve one of the parametric equations, which by the way are x equals 2 sine t and y equals 3 cosine t, solve one of these for t and substitute into the other? It's not impossible. I wouldn't do it though, because solving either one of these is going to involve an inverse trig function, which we would have to substitute into the trig function, and although not impossible, it's just not desirable from an algebraic perspective. Try it if you don't believe me. We can't find a strong connection or an obvious connection between these two like we did in the previous video, where one of them involved cosine, the other one involved cosine squared. So we did a real quick swap out for cosine of t and we changed it to x. But we can use another strategy, and this one is fairly common. If your parametric equations, your parametric equations involve trig functions, the strategy is to use a trig identity. Well, just use a trig identity. Now, you're in Calculus 3. You've seen lots of trig identities, but there are some that you should just know. Your reciprocal identities, such as secant equals 1 over cosine. Your quotient identities, such as tangent equals sine over cosine. And your Pythagorean identities, such as 1 plus tangent squared equals secant squared. So, do you know a trig identity that connects sine and cosine? You should, because it's a Pythagorean identity. That Pythagorean identity that we're going to use is sine squared, in this case sine squared t, plus cosine squared t is equal to 1. Because I'm talking cosines and sines. Now, in order to use this identity, we have to know what sine t equals and cosine t equals. Right now, neither parametric equation reads that, but it wouldn't be that hard to make them say sine equals and cosine squared equals. So find a trig identity that connects the trig functions, isolate the trig functions. So if x equals 2 sine t, then sine t is equal to x over 2. And similarly, if y equals 3 cosine t, then cosine t is equal to y over 3. And now that we know what sine t and cosine t equal, we can insert them into this trig identity by replacing the sine with x over 2, but the sine was squared, so is this. The cosine with y over 3, but the cosine was squared, so is this, and setting it equal to 1. This should look familiar. It might look more familiar if we distribute the square across both sides of the fraction and get x squared over 4 plus y squared over 9 is equal to 1. If you recall from Thursday, that's the equation of an ellipse. And remember, if it's centered at the origin because there's nothing being subtracted from the x and the y, then you can locate your x and y intercepts by simply taking the square roots of the denominators. Since the number under the x squared is 4 and the square root of 4 is 2, our x-intercepts on this ellipse are going to be at 2 and negative 2. And since the number under the y squared is 9 and the square root of 9 is 3, our y-intercepts will be at 3 and negative 3. So this is going to be an ellipse. Now you might be worried that I thought sine and cosine had restrictions, they can only stay between 1 and negative 1. And you're not wrong, but this x component function, sine, had a 2 in front of it. So it changes the amplitude from 1 to 2, which means my x's can stay between 2 and negative 2, which they do. And similarly, the amplitude of cosine is 1, it goes up to 1 and negative 1, but this has a 3 in front of it, which triples the amplitude, meaning that the y component, the y coordinate on the graph, can go between 3 and negative 3. So it's doing what it ought to be doing. The only thing we're missing, however, is the orientation. To find the orientation, we do need to locate some points according to the time at which they occur. In other words, we need to make a partial table, make a conjecture about the orientation, and then verify it with some further evidence. Let's just put in t equals 0 and see what happens when we put that into our vector function. And we'll just talk it out. Sine of 0 is 0. 2 times 0 is 0. Cosine of 0 is 1. 3 times 1 is 3. So at time equals 0, we're at the vector 0, 3, which is up here. Here's where time is equal to 0. Let's fast forward to pi over 2. I'm thinking unit circle. 0, pi over 2, pi if necessary, 3 pi over 2 if I want to. At pi over 2, let's see what happens. When we put pi over 2 here, sine of pi over 2, meaning on the unit circle, what's the y coordinate at the top, is 1. Sine of pi over 2 is 1. 2 times 1 is 2. However, at the top of the unit circle, cosine of pi over 2 is the x coordinate, that's 0. 3 times 0 is 0. So at time equals pi over 2, we're at the vector 2 comma 0, which is over here. So our orientation seems to be going clockwise around this ellipse, but let's make sure that it doesn't do like that parabola chunk did, where it went back and forth. Let's just crank out a couple more values. A next good one is pi, or another good one is pi. There's some good ones in between. If we put pi here, sine of pi is 0, so 2 times 0 is 0, but cosine of pi, the x-coordinate on the left side of the unit circle, is negative 1. 3 times negative 1 is negative 3. Well, that's down here, 0, negative 3. That time equals pi, I'm down here. Well, let's make a conjecture where we're going to stop next. If we continue this pattern of going up by a half pi each time, and look at where we're going around this ellipse, where would you predict that we land next? Probably on this westernmost point. Right now it's a conjecture, so I'll put a question mark on it. But let's verify it and see if our suspicion is correct by substituting 3 pi over 2 into our vector function. 3 pi over 2 on the unit circle is at the bottom of it. At the bottom, sine is the y coordinate, which is negative 1. 2 times negative 1 is negative 2. And at the bottom of the unit circle, the x coordinate, the cosine value, is 0. 3 times 0 is 0. Negative 2, 0 is exactly where we thought it was going to be. This orientation will just keep going clockwise around this ellipse as long as we let the clock run. So yeah, sometimes it's easier to graph the space curve generated by a vector function by first eliminating the parameter, which in this case we did thanks to a trig identity connecting these two trig functions, and then looking at the rectangular equation and saying, I know what that is, that's an ellipse. But you do have to be careful, because remember in the previous example where we had the vector function cosine t, cosine squared t, and when we eliminated the parameter, we got y equals x squared. It was not the entire parabola, because the component functions each had a range that was limited. The range of cosine can only be between negative 1 and 1, which is why this parabola only oscillated between negative 1. And the range of cosine squared is only between 0 and 1, which is why this parabola got cut off at 1. But the clock kept running and you had to go somewhere, so you just have this oscillatory motion. But had you just said graph this, you wouldn't have gone, look, it's going back and forth like a skater in a half pipe. You would have drawn the whole parabola and you would have been wrong. So using a table of values will often identify when the graph of a vector function is not the entire graph of the rectangular function like this one, but a portion of the graph. That's usually caused when your component functions have limited ranges, as opposed to these, which do have limited ranges, but those ranges were limited by this ellipsis graph anyway. The x's were never going to go past 2 or negative 2, nor were the y's going to go past 3 or negative 3. It dawned on me at the beginning of this video that what I've done is actually reviewed some Calculus 2 stuff from Chapter 9 of the textbook that we're currently using. So if the parametric equations and the graphs are something that you're not as comfortable with, I highly recommend going back in your book, going into Chapter 9. I would look at, well, the beginning. I would look at section 9.1. And then on class Tuesday, we'll talk about doing Calculus 2 vector functions. Don't worry, we're not doing all the vector calculus yet. That's what the rest of the course is for. But we'll talk about simple things like what it means to take a limit of a vector function, which is exactly what you think it is, what it means to take the derivative of a vector function, which would be exactly what you think it is, what it means to integrate a vector function, which is exactly what you think it is. So do us all a favor, read through 10.7, come to class prepared to start and finish 10.7. I don't want to say quickly, but it's not going to take the entire class period. Then we're going to jump into 10.8.